Introduction to sound waves. 1. Sound waves are produced by vibrating objects such as the musical instruments. In musical instruments, the source is set into vibration by the musician striking, plucking, bowing, or blowing the instrument. String instruments produce sound using a vibrating string. When the string vibrates, the vibrations are transferred to the wooden body of the instrument, where the sound is amplified acoustically. The sound is then transferred from the instrument's wooden body to the surrounding air. Click on the string instrument. Instruments such as the flute, trumpet, and pipe organ produce sound using a vibrating column of air. The musician blows across a hole in the flute to create a vibration in the air column. The flute is crafted so that these vibrations will produce a loud and pleasing sound. Click on the wind instrument. Energy from the vibrating source is transferred to the surroundings by sound waves. The frequency of the sound wave is the same as the frequency of vibration of the source. The normal audible frequency is from 20 Hz to 20 kHz, and the speed of sound in air is about 330 meters per second. Click on the percussion instrument. In this lesson, you will be able to understand sound as a form of longitudinal wave, understand the propagation of sound waves in terms of pressure variation and displacement, interpret the equations for displacement, y equals y naught sine omega t minus kx, and pressure P equals P naught sine omega t minus kx plus pi over 2. Describe quantitatively the formation of standing waves along stretched strings. Use the formula for the frequency of the sound waves produced along stretched strings. Click play to move the hand. The end of the slinky oscillates backward and forward horizontally. The coils at some regions of the slinky are stretched wide apart, and in the region in between the coils are compressed. Click step through to step through one cycle of the wave. Observe a compressed region moving away from the hand in the direction of propagation of the wave. What type of waves are produced as one end of the slinky oscillates back and forth? Answer: a series of longitudinal waves are produced. What is the difference between this wave with the transverse waves? Answer: in the longitudinal wave, the displacement of individual particles is in the same direction as the direction of propagation of the wave. Click play. The formation of a sound wave in air is very similar to the action of the slinky. As the diaphragm of a speaker vibrates back and forth, it alternately compresses and rarefies the surrounding air. These regions of high and low density propagate away from the speaker with the speed of sound. Click step through to step through a cycle of the wave, frame by frame. Observe the formation of compressions when the diaphragm of the speaker is extended and rarefactions when discontracted. Observe a compression moving along the wave in the direction of propagation. Click pause and click on one of the red particles. Now restart the wave and observe the motion of these particles. The motion is horizontal along the direction of propagation. Both the speaker and the slinky produce longitudinal waves. Sound waves are longitudinal waves. To restore the original color, click clear. What is the effect of increasing the amplitude on the compressions? Answer: the particles in the compressions are squeezed closer together when the amplitude is increased. What is the effect of increasing the frequency on the compressions? Answer: consecutive compressions come closer together. The wavelength of the sound wave decreases. Increase the frequency and amplitude of the wave to the maximum using the slider and click pause. Click on the particles in the middle of two consecutive compressions. This will highlight them in a different color. Restart the motion by clicking play. What do you observe about the motion of air particles in consecutive compressions? Answer: the particles in the middle of two consecutive compressions oscillate in phase with each other. Click play. When the speaker diaphragm oscillates, a progressive longitudinal wave is generated. It can be seen that as the air particles oscillate to and fro about their undisturbed positions, compressions and rarefactions travel to the right. In the slide, you can see an interactive model of a longitudinal wave and its corresponding displacement distance graph. Now, click Label. What do you observe about the displacement at the center of compressions and rarefactions? Answer: the displacement of the air molecules at the center of each compression and rarefaction is 0. In the slide, you can see an interactive model of a longitudinal wave and its corresponding pressure distance graph. Use the interactive model to find the pressure at the center of a compression and rarefaction. Now, click Label. The crowding together of the air in a compression causes the density and pressure of the air to be greater there than normal. Both are maximum at the center of a compression. Conversely, density and pressure have minimum values at the center of a rarefaction. The ear responds to pressure changes rather than displacement. The variation of pressure for a very loud sound is 30 pascals. This is very small when compared to the normal atmospheric pressure, which is about 10 to the power 5 pascals. In fact, the ear can detect pressure variations as little as 2 times 10 to the power -5 pascals. The animated graph above shows the tiny pressure changes relative to normal atmospheric pressure, which is detectable by the ear. When is the pressure at a particular point A maximum and B minimum? Answer: the pressure is maximum when the air particles are squeezed together in a compression. It is minimum when the air particles are stretched apart in a rarefaction. Click play. The above interactive model illustrates the phase difference between pressure and displacement. From the graphs, we can see the phase difference of 90 degrees between pressure and displacement. Increase the frequency slider to compare the two graphs with the motion of the air molecules. When does an air molecule have zero displacement? Answer: an air molecule has zero displacement when it is at the center of a compression or a rarefaction. Click Equation. The equation for displacement is y equals y naught sine omega t minus kx, and the pressure is P equals P naught sine omega t minus kx plus pi over 2, where omega equals 2 pi f F is the wave frequency, Y0 is the amplitude of wave, P0 is the amplitude of pressure change, and K is a constant. What is the phase difference between the two graphs? Answer: the phase difference between the two graphs is pi over 2 radians. Summary: sound wave is a longitudinal wave which requires a medium for its propagation. Air at the centers of compression and rarefactions has zero displacement. The pressure is maximum at the center of compression and minimum at the center of a rarefaction.